What if a single power cable stretching thousands of kilometers beneath the ocean could transform the future of energy forever? Imagine harnessing the endless sunshine of the Australian Outback and delivering that clean electricity directly to one of Asia's most advanced cities, Singapore. It sounds like science fiction, but this is one of the most ambitious engineering projects ever conceived. In today's video, we'll explore the world's longest undersea power cable, a megaproject that aims to connect Australia and Singapore through more than 4,000 kilometers of cutting-edge energy infrastructure. From massive solar farms in the desert to deep-sea cable installation challenges, this project could redefine how nations share renewable energy across continents. How will it work? What engineering obstacles stand in the way? And could this become the blueprint for the global energy networks of the future? Stay with us as we dive deep into one of the most fascinating megaprojects on Earth. Welcome to Datascope, where we uncover the world's biggest engineering marvels, infrastructure megaprojects, and technological breakthroughs. The project highlights the stark contrast between the vast, sparsely populated northern territory of Australia and the densely populated island nation of Singapore. Singapore, with its nearly 6 million residents living in a limited area, faces challenges in developing large-scale domestic power sources. This difference lays the groundwork for the Australia-Asia Power Link, which envisions Australia as a major exporter of renewable electricity through subsea cables. The plan involves transforming the Australian desert into a massive power station and constructing an extensive cable route over 4,300 kilometers to Southeast Asia. Observing the Northern Territory from above, one would note that the project's starting point is in a region with minimal infrastructure and population. The Berkeley Solar Precinct, which serves as the energy center for the Australia-Asia Power Link. This complex is set to span over 12,000 hectares of desert land in a region known for its high solar irradiation levels. Once operational, it could generate approximately 6 gigawatts of stable, clean electricity, making it one of the largest solar power plants in Australia. Engineers face the challenge of deploying millions of solar modules using unprecedented industrial-scale installation methods. Initially, the proposal aimed for an even greater capacity of 20 gigawatts, matching the output of multiple large-scale power plants. I understand that the Berkeley Solar Precinct serves as a vital power station in the desert, contributing to the transcontinental transmission system after some adjustments were made to its scale. I recognize that the creation of a massive solar farm alone doesn't fully address the need for stable electricity supply for Darwin and Singapore without a significant storage solution. I learned that the Australia-Asia Power Link incorporates a substantial energy storage complex, planned to hold around 36 to 42 gigawatt hours, marking it as one of the largest in the world. I see that this storage capacity vastly exceeds that of the Hornsdale battery system, and it functions as an energy buffer alongside the solar precinct. I note that the project also includes the construction of a nearly 800-kilometer high-voltage transmission line to effectively transport power from the desert to the northern coastline. Part of the electricity generated will supply Darwin and the Middle Arm region, intended as a clean energy industrial hub for northern Australia. The remaining power will be transmitted offshore after being converted at a large-scale HVDC converter station in Darwin. This conversion is essential to minimize energy losses during long-distance transmission beneath the ocean. Once converted, the electricity will reach the Landsea Transition Facility northeast of Darwin, connected to a subsea power cable route over 4,300 kilometers long. Manufacturing this extensive subsea power cable represents one of the most challenging phases of the project. At this scale, cable manufacturing transforms into an independent industrial megaproject that spans several years. Unlike conventional power cables, subsea transmission cables are produced using a distinct principle that requires the elimination of every possible defect during the manufacturing process. Once laid on the ocean floor at great depths, any needed repairs become exceedingly complex and costly. My process starts with a central conductive core, typically made from highly purified copper or aluminum, which is melted and drawn through precision molds for uniformity. After heat treatment to enhance bending resistance, the conductors are stranded and shaped to ensure stability and manage tensile forces during offshore transport and installation. Begin with the extrusion stage for the high-voltage XLPE insulation layer, where the metallic core is enveloped in molten polyethylene to create a protective layer. I understand that even the slightest air bubble or crack can lead to the rejection of an entire cable section, as it poses a risk for future catastrophic failures. Alongside the power transmission layers, I integrate optical fibers for real-time monitoring, ensuring they can bend without stress during installation. I conduct a thorough inspection of the system using laser-based testing to confirm minimal signal transmission losses. Finally, I reinforce the outer cable layers with polymers and steel armoring, enhancing protection in coastal areas while optimizing for weight and pressure resistance in deep waters. Before deploying the cable route, I must survey the entire corridor of over 4,300 kilometers from Darwin to Singapore using multi-beam sonar and seabed seismic equipment. The goal is to identify deep trenches, underwater rock formations, tectonic fault zones, and strong ocean currents to optimize the cable route. I also need to ensure that the route avoids major shipping lanes, fishing areas, and environmentally sensitive marine zones, particularly in Indonesian waters. Only after completing this survey can I begin the subsea cable installation process on the ocean floor. Observe that specialized cable-laying vessels deploy each cable section along a designated engineering corridor while conducting cable jointing, burial, and inspections. The electricity travels over 4,300 kilometers through the subsea cable route to reach Singapore, with each kilometer of cable weighing between 100 to 130 tons. This extensive deployment necessitates the use of large, specialized ships analogous to those in the global subsea cable sector. In shallow coastal areas, cables are buried in pre-excavated trenches to minimize risks from anchors and fishing activities. The project in Australian waters will take about 2 months per cable route and involves complex coordination across countries before connecting to Singapore, ultimately creating one of the longest transoceanic power transmission corridors ever built. If a subsea power cable route fails, locating the fault quickly becomes crucial. I dispatch a specialized repair vessel equipped with positioning tools and remotely operated vehicles to the damaged area. Since repairs at great depths are nearly impossible for humans, ROVs are used to lift the damaged cable section for repair on the ship's deck. Engineers then splice the cable while ensuring proper insulation and sealing to maintain functionality. Occasionally, saturation divers are sent for shallower repairs, but every operation is costly and a race against time to prevent further economic loss. Unlike conventional domestic power projects, I am involved in the Australia-Asia Power Link, a cross-border energy system spanning over 4,300 kilometers to Singapore. This project relies on both engineering and policy coordination among several countries, with significant challenges in Indonesian waters. After extensive negotiations, Indonesia has supported the project with economic cooperation commitments totaling around $2.5 billion. In 2023, the project underwent financial restructuring, emphasizing the importance of political stability, regional collaboration, and long-term investment in transcontinental energy initiatives. Upon completion, the Australia-Asia Power Link will establish a new electricity transmission corridor and potentially lead to a renewable energy export network across the Asia-Pacific region. The Australia to Singapore Undersea Energy Highway is more than just a power cable. It's a glimpse into the future of global energy. If successful, this groundbreaking megaproject could prove that clean electricity can be transmitted across oceans, connecting nations through renewable power like never before. What do you think? Could massive undersea power networks become the next generation of global infrastructure, Or are the engineering and financial challenges simply too great? Let us know your thoughts in the comments below. If you enjoyed this deep dive into one of the world's most ambitious engineering projects, don't forget to like, subscribe, and turn on notifications so you never miss our next exploration of the planet's biggest megaprojects and technological breakthroughs. Thank you for watching Datascope. We'll see you in the next video.